So the last talk of this session is by Johan Euphrosine
Okay, désolé.
about accelerating open source silicon ecosystem. Please welcome him.
Okay. Bonjour. Hello. My talk is about accelerating open source ecosystem with Jupyter Notebooks. So it's going to be in two parts. First, I will explain the open source ecosystem we're trying to bootstrap with Silicon, and then I'm going to explain how Jupyter Notebook helped us doing that. So first, a few words about myself. My name is Johan Euphrosine. I go online by Propi. I joined Google a little bit more than 10 years ago. And I'm a developer relation engineer, meaning that I'm focused on making Google technology accessible to all developers. I've worked on a variety of products, ranging from cloud to mobile to embedded. And recently, I've joined a new team at Google called the hardware toolchain team. And that was a new thing for me because I was involved a little bit with IoT or embedded things, but never with actually manufacturing chips. So keep in mind when I'm going through that I'm also very new. I learned most of that stuff less than 1 year ago. And so our team mission is to make custom silicon easier to build for everyone at scale, just like software. So the vision is to have something like this. So you might be familiar with your an open source compiler called GCC. It has a -o flag to choose the optimization flag. And sometimes there is just so much things you can optimize in software. Sometimes you have to actually manufacture a dedicated accelerator to optimize further. And currently, the gap that you have between that, it's almost a new profession. So as a software engineer, you can't really produce the hardware that will optimize your software further. So our team vision is to make that true, so that you could, with your tool that you use as a software engineer, could optimize further in hardware and design the hardware and the software together. We are not quite there yet, but that's the vision. And so when we look at that goal 2 years ago, and we look at if it was possible at all, we found out that there was missing pieces. So there was this paper published by the team founder, Tim Ansel, at ICCAD in 2020 called The Missing Pieces of Open Design Enablement. And he identified 2 years ago that there were 4 pieces missing for making that vision true. First, we needed open source PDK, because 2 years ago, most of the PDK were under NDA with the foundry. So the PDK is the lowest level of the API that you need to manufacture a chip. It's basically the piece of data that describe the foundry process. So if you don't have access to that, you can't have access to the foundry, you can't manufacture a chip. And all those PDK were, as of 2 years ago, under NDA. So meaning that as an individual developer, you couldn't even dream to manufacture a chip because you didn't have access to the process. The other thing that was missing, or at least not quite there yet, was the tool. Most of the tools that are used by the industry are proprietary, and there was open source toolchain there, but with with a lot of limitation and very few users, because the lowest level was not accessible to there, and the level of people that were actually using open source tool was quite low. And then as a byfactor of that, because the lower level of the API is proprietary or under NDA, and the tools are proprietary themselves, there was not a lot of open source IP block that you could actually reuse, because most of them were either tied to the tool or tied to the PDK. And last, but not the last, and maybe the more important one, is that it costs a lot of money to manufacture silicon, and it costs a lot of time. So you're looking at 3 to 6 month timeline from the moment you submit the design, from where you receive the part. And you're looking at tens, if not hundreds of thousands of dollars, or sometimes millions of dollars for a single run. So we went on a mission to try to fix some of those in order to build an open source silicon ecosystem. So the first thing that we've done is that we've partnered with some of the foundry, like Skywater and Global Foundry, to convince them to open source the PDK for their older technology. So those are 100 nanometer and 180 nanometer technology. So those were things where the first Pentium were built. So, but those are totally fine to learn and totally fine to experiment for, and totally fine to prototype for startup for IoT products. So that was a big achievement to convince them to open source their PDK under an Apache 2 licenses and to put them in GitHub. The interesting thing that we saw this year is that for the first time, there was a foundry in Austria called IHP who open sourced their PDK without having us told to them at all. So they went on their own, they've seen what we've done with Skywriter and Global Foundry, and they went ahead and open source their own PDK. And that's like the Foundry trying to reach out to more customers and realizing that opening their PDK will help them do that. So that was a good validation of what we were trying to do. And this year, hopefully, we hope that we can release a more advanced PDK for 90 nanometer technology with Skywriter. So for the toolchain, there were many tools as part of the ecosystem, some of them that were already there, some of them that were developed by Google. So for example, Google were developing a high-level synthesis toolkit that I demoed at one of the Lightning talk 2 days ago. But there was also like tools that were there for a long time, like for example, Euphrosine is a well-known tool for synthesis that's very used a lot inside the FPGA, but also in the ASICs world. There was this tool called OpenRoad that we founded to get better. That's for doing the place en route. So it's taking like the component that got inferred by Euphrosine and trying to place them on a chip and do the routing between them. And then there is like the GDS streaming and DRC tools called Magic and Keliot that finally do some final check and produce a final file that you submit to the Foundry. So you see here you have like, we managed to build a toolchain all done of open source tool that allow you to go from a high-level description of your design down to a file that you can actually manufacture. But there's still a problem for manufacturing. Like I said before, it's still called a loss of money to manufacture. So for 2 years, we've been running like this open APW shuttle program. So the rules are very simple for this shuttle program. Like as long as your design is open source, as long as your design is reproducible with the open source tool, Google will pay for the manufacturing. And so we will select like 40 projects out of all the projects submitted for each run, and we'll manufacture them at no cost. And at the end of the run, you get a little board like this to test your project with a dev board underneath, and you get a collection of chips like this that you can solder yourself if you want. And so we've run 9 of those shuttles, and you can see at the very beginning the engagement was quite low, but we got as many as like 140 submissions to a single run as of last year. And I guess the most important thing is that like the cumulative aspect of it. Like if you sum up like all the projects that got submitted to this program over time, that's more like 750 piece of open source silicon that have been produced as part of that. So that's like a big side effect. And I'd say the biggest side effect that we had is that it made the tool way better. Like the tool, like they were, like this toolchain I was showing as of 2 years ago was nowhere where it is right now. It's becoming close to the level where we can start using it internally at Google as well. So it's very good. As long as we keep the shuttle running, the tool will get better. And I think that's also the biggest insight from this is that you can't really make the tool better if there is no user. And so, yeah, there is also a very kind of diverse community who participated to this shuttle. You can see here, like, people from India, from the United States, from Japan, from Europe as well. I don't see a lot of people from France. I think there is maybe one user on the 5th shuttle who was from France, but it's definitely our fault for not doing enough outreach in this country. And currently, like, people are busy trying to make their hardware working. So it's a snapshot of like what people are doing for MPW2, which was the second run, and they are all like on their benchtop trying to find out if it's working at all, like complaining, like sometimes taking some thermo picture to see if the chip is not too hot. And there was like a lot of interesting projects submitted there from like people that have nothing to do with hardware before and that were super happy to do their first chip, down to people who were in the hardware for a long time but were amazed that they were able to do that from their laptop. For me, like the highlight of this particular MPW run was like this project on the right, who like people manufacture their own FPGA fabric on a chip. So they made a custom FPGA with a custom FPGA toolchain, deployed their own gateway on it, and managed to get a demo working on the screen. That was very impressive because so many things could have failed across all of those layers. And so I want to talk now a little bit about what inside the Jupyter ecosystem helped us to be successful there. So first, like the Conda ecosystem. So we started realizing that the big barrier of entry for people were to just install the tool to get that toolchain running. And before we started that, like most of the default way of running those tools was to compile them from source. And those could take a long time for some of those from those tools. So making sure that we had Conda packages for all of those tools with properly set up dependency. So here you can see I'm just depending on OpenLane and the PDK is bringing all the tools that I mentioned before. And yeah, that was a really great way for us to accelerate this. And the other thing was that we also discovered is that notebooks are a fantastic tool to teach people like how to use those tools. Like those tools, like they need to be meshed together into a very specific way, and like it's this knowledge is not captured at all anywhere. Like there is not a higher level documentation that capture all of that, and that was very confusing for people that were used to proprietary tool and wanted to try the open source tool that were already part of the industry, but that was also confusing for people from the software world who had no idea of how to use those tools together. So we started putting together a collection of notebook to achieve like common task that you have to do over like the fabrication of silicon. And so we have this repository where there are like a lot of notebooks in there that try to capture that. So the first thing was for silicon simulation. So when you get a PDK, you get a set of cells that the foundry is capable of manufacturing. You get a set of specification of layer, and you want more to experiment with those cells to figure out like how they work, how do they react to electricity. And so I want to show you quickly what it looks like in that notebook. Maybe a little bit bigger. Yeah. So you can see first I have like, so maybe a little bit smaller then. And let me hide this gigantic, yeah, okay. So first I define like the environment that I need inside an environment.yml, and I install the required tool. And then I'm drawing basically things on the silicon layer. So I'm drawing like two things on the N diffusion and polysilicon layer to basically do a transistor. So I'm like doing a little transistor by hand there. And then, like with a library called PySpice, I can write some Python to simulate what happens when I send like some current to that transistor. And you can see here that I build a little inverter, as I have the voltage ramp up here, like the voltage there is inverting. And being able to see that, being able to draw that inside the notebook for someone that has nothing to do with silicon, like I was like 1 year ago, that was very eye-opening. And so let me try to show you another example. It's going to be, so the other thing was for running workshops and teaching silicon design in general. So here I've shown you a very low-level aspect of simulating a single transistor, but what if you have an idea of writing a simple algorithm and you want to run it through that toolchain? So in Japan, we were able to run like a series of workshops with the University of Tokyo, targeting specifically CS students, so students for computer science that have nothing to do with silicon, and we were able to use notebook to show them how to do this. So let me show you briefly what it looks like. So same again, a Conda environment to install the package. And here I have like a simple design that's using the high-level toolkit I was mentioning before. So here I'm doing like an adder function. So it's a very simple, it's like the simplest design I could think of. It's a chip that's adding 2 bits. So you ship it 2 input, and it will put up on the output. It will output like the sum. And so you can see I can write them using like just a regular programming language, much like I would write it in software. And I can also write tests for it to verify that it works even before thinking of mapping that to a chip. And like the other interesting thing is that could be a function that I can reuse as well. And so here I want to make a bigger chip actually, that one that has like 8 input and 8 output. And I can define how those 8 output and 8 output like map to my adder function. And so I can run this with a toolchain, get an intermediate representation, and start running it through the tool. So there is a tool that converted to Verilog, which is a different language that's more low level, that describes like the relation between all those components, and that's compatible with the rest of the open source silicon toolchain. And then I can run it through a series of syntheses for planning and routing. And I want to show you quickly there what happens when you turn that to a chip. So first, you will try to map it to the underlying technology. So that's like something called synthesis. And then like the code that we've written that's adding 2 bits will become gate. So now we have a XOR gate and an AND gate So the XOR gate will be for the lowest bit of our addition, and the AND gate will be for a higher bit of our addition. And then I could run that through the floor planning. And once I run it through the floor planning, I could look at what's being there. And so you can see my chip boundary have been defined. And I have my XOR gate and my AND gate there that are at the very bottom because they are not placed yet. And then we can raise it through placement. And then suddenly, like those gates are in the middle. You can see them. They are placed in the middle now. And then I can run them through routing. And then now, if I remove like the top level layer, I should be able to see the gate together and some wire between them, and trace like the wire from the input down to the wire to the output there. And so, like being able to do that in a browser without having to install anything and using like a Jupyter Notebook was really both convenient for the workshop because people were able to get started quite quickly, but also very eye-opening for some people that were already in the field because usually because they were working with proprietary PDK before and proprietary tools, they often, for example, at the University of Tokyo, they had like one computer where you could do that had to be used by everyone in their lab. So, oops. So let me show you other thing that we did with notebooks, if I still have time. Something else that we saw is that like people from that community, especially at the academic field, started picking up on those notebooks for doing publication. So in the semiconductor world, there are like two big like conferences that are very prestigious called ISCCC and VLSI Symposium, and those two conferences are usually out of reach for most of the doctorate inside the field or even the undergrad. Like they can only attend it, they can't really present at them because it's very competitive. So what the IEEE Solid State Society did is that they organized a notebook contest where people will, if they write a notebook for this context, they could get invited to that competition, to this like prestigious conference to present their work. So it both achieved like getting more access to that conference to people who couldn't really afford going to them before, and also getting more representation of reproducible research using notebooks. And so there was a variety of notebooks that got submitted to this repository, and so it was very great to see some validation that notebooks could be used inside that field. Another aspect of this is doing optimization using notebooks. And so because I'm working at Google, we also have a platform called Google Cloud, and we were able to run a lot of parameterized job exploration to try to optimize notebook. And so you can see here on the left, like I'm running like jobs to try to optimize like the area and the density of a given chip and trying to minimize power. So each of those dots that you see here is a notebook that I can run with different parameters, and I can extract like the different like layer that got produced there, and extract the data as well, and get them to analyze it with Panda. If we want to, if we still have time, yeah. If we want to take a look at how it works in practice, I can show you very quickly. So, yeah, okay. So, like first, like people will define like the flow parameter using the peppermill syntax. So they will put like this cell is actually tagged with parameters, and it defines like some default parameter for. Let me go back to this one actually. It defines some default parameter for the flow. So here I'm saying that by default I want 100. Micrometer for the width, and I want 80% for the density. And then I can run the flow and see, validate my experiment and see it's working for those parameters. So that's like the first step is to define like a notebook that encapsulates like your experiment. And at the end, you will dump the flow metrics and then say which metrics you want to report as the output of your notebook. So here I'm saying the total power is what I want to report. So now my notebook acts like a little function. It can take parameter and report a result. And so once you have that, you can do parameter tuning. And so here I define like the type of machine that I want to leverage for doing this parameter exploration work. And I define like the parameter spec that I want to explore and the metrics that I want to minimize. And here I'm abusing like something that is there in Google Cloud that's actually meant to train ML model and optimize them initially. It's actually, it works with anything. So I disguise like my EDA job, so my silicon job, into a ML training job. And I'm just like specifying the parameter that I want to optimize and the metric that I want to monitor. And then I could start like 10,000 of those. And the nice thing is that like each of those things will run paper-mill. So each of those things will actually create a notebook. And so at the end of the experiment, I will get like thousands of notebooks that capture this. And because this notebook use like a little package called scrapbook, I will be able to attach like metadata to this notebook that captures some of the execution state. And so the nice thing about that is that I can inspect like the individual run and see why a given run failed. So for example, this one, we can see that it didn't quite work well. And if we took a look at the end, we can see that, yeah, it didn't have, the current area was too small. That's what it tells. And if we look at the area, like effectively, like it was like way too small to have like the default that we were using was 175. The area that got chosen here was half of that. So there was not enough space to put all the gate. And I could look, and if I aggregate like all of that output, you can see here, I can read like inside the data frame like this data that I added to each of those notebooks and try to sort them to see what was the most successful experiment. And here we see like the trial like 230 was very good because it was not consuming a lot of power. It has a reasonable die area. And I can take a look at this particular experiment and reproduce it and see like the actual layout for it, and like share it with the researcher and say, yes, this is the best parameter that we should start to base the work on. So that was one example of how also like using notebooks could accelerate like optimizing your flow. The other thing that we've shown, now that we are starting to get some silicon that I've shown you back from the foundry, is that we can use notebook to characterize the silicon that we get back. So when we fabricate some silicon, the chip will be usually equally spaced on the wafer, and between like those line, between those chips, the foundry will put like little test structure that you can use to validate the process. And so we started like working with university to ship them those wafers so that they can measure like the behavior of the device and verify that the modeling information that we have, so the first thing I've shown you, like the simulation at the beginning of the transistor, was actually confirming to what we were getting back from the foundry. And our hope is that like, by getting more modeling experts contribute to that repository, we could improve the model. And instead of having the PDK be this static thing that you get from the foundry that you take for granted, become something that actually, as we manufacture more chip, like the PDK will get better. And lastly, before I also wanted to show how notebooks could be used for silicon bring-up. So we get like, that's what we ship back to the user, but they have to test now that their device their design actually behave like they originally designed and that the silicon is actually working. And it's fairly involved usually to bring up some silicon because it requires like running a series of commands on your host to accumulate the data, running a series of commands on the test device, and maybe running some command on an intermediate device that will like trigger and signal the device that you want to test. And I found like a very nice module called iPi device that's really great for doing this kind of work. And so I just wanted to give a shout out to it here, that it allows you to connect to the serial port over a board that's running MicroPython. And then it allows you to send some cell for execution directly on the device itself. So rather than executing on your host, when I click play here, it executes on the device. And so, and if I tag a cell with local, it runs on my host computer. So now I can have a single notebook that both describe what needs to be run on my computer in sequence on what to be tested about the device, and I can validate something. So here, like the device I was trying to validate is one of the simplest devices that we got on that shuttle, which is a Fibonacci number, a Fibonacci sequence generator. So what it will do is that it will output on 30 pin the sequence of the Fibonacci number. And so I connected over the device, I configured its I/O, and then what I was I'm specifying that I want all the I/O be configured as output. And then I run a little firmware on a RISC-V that's embedded on every single chip that we manufacture that activates the project and start it. And then once the project is started, I blink the LED to know that it's working. And what I quickly wanted to show there is that like we were able to run some MicroPython code that was attached to that device, and that basically clock the device on every clock cycle and capture the I/O to verify that they were matching the Fibonacci number. So I got a series of numbers there that I assemble inside the data frame. And then I compute the real list of Fibonacci number on my host now to verify that it's matching. And then I was able to plot like in a data frame like which I/O were working and which weren't. So I was able to see that that chip is actually defective. Like for like the lower level I/O, they are almost wrong. And so that's also like a good thing is that now I can share with someone else and tell him like this is how we bring up my chip. This is how we verify it works. And more importantly, because we ship 50 of those chips to each user, they could put another chip on their test harness, rerun the same notebook, and get a different result, and start archiving and correlating which chip are working and which are not. And so, yeah, let me go back to the presentation if I manage to. Yeah. And the last thing I wanted to mention briefly is that we can also use Jupyter Notebooks for silicon inspection. So I actually went to the Swiss light source last week, and they were taking some of those chips that we manufacture and running it through synchrotron to do IR imaging. And so that's the kind of thing that they get with the raw sensor data. And that's the thing that they try to reconstruct, which has like the actual image of the different layer. And that's the design data that we are trying to correlate that against. So I have an IP MD5, but I'm running out of time here. But that's currently where we're at. We are also partnering with a researcher to try to kind of correlate the data that they do with the imaging with the design data. And the beautiful thing here is that because the design is open source, we can actually verify that the foundry manufacture what we gave to them. And so, yeah, I invite you, if you're interested into that field, to join like the open source silicon community. We have a community of more than 4,000 members on Slack, and there is this portal that describes like the program and what we do. And if you just search for build open silicon, you should find a blog post that describes the high-level goal of the project. So, yeah. Thank you.